Hello, everyone, and welcome to another wonderful day of PChem. So today, I figured it's been a while since we've talked about rotational motion. It's time for a quick review of all the various types of rotational motion. And specifically, we're going to look at how it relates to rotational spectroscopy. So first of all, just as a reminder, rotational or microwave spectroscopy, because that's the region of the UV of the spectrum it shows up in, works by essentially using a photon to increase the rotational motion of a molecule. And the description of this rotational motion can be subdivided based on the symmetry of the molecule in question. So here's where we're going to bring in a little bit of our knowledge of symmetry. And it's split into four major categories. The first of which is linear spectroscopy or linear molecules. So these are going to be molecules that have C infinity axes. When I have an infinity axis, it usually means that all the molecules are going to be strung along 1 degree of motion. And as a consequence, it means that I really have no rotation about this single axis, and all the rotation has to occur in the other two planes. This simplifies the system a lot, as both of these planes are identical, whether as in this case, it's the z plane or the x plane coming out towards us. Rotation in these directions are always end over end and are pretty much degenerate with no motion occurring in that third dimension. So it's a nice two-dimensional problem, keeps it fairly simple. However, we also have spherical molecules. These are going to be molecules that belong to the tetrahedral, octahedral, or isosahedral point groups. So in these cases, motion in all three directions are going to be equivalent, which means that I only still have to deal with one type of motion, but now I have a full three-dimensional problem, which complicates the system a little bit. Next up, we have symmetric molecules. So these are going to be molecules that possess two identical rotations. So good examples here are the D point groups, so DNH and DND, as these groups have one principal axis of rotation, usually highly symmetric, and then multiple C2 rotations in the other direction. So you can think about one highly degenerate axis, and then the remaining axes are always end over end. So you can think about this as a linear molecule with a little bit more structure, so we can introduce a full rotation about that main axis. Then finally, we have asymmetric. This is pretty much going to be our phrase for everyone else. So in asymmetric molecules, all three types of rotation are independent. And so we have to solve this problem kind of by hand, no real shortcuts. So not too surprisingly, we tend to focus in on these first three, where we can use symmetry to help simplify the problem. Let's go ahead and start by focusing in on our nice linear system. So linear molecules can be diatomic or triatomic, and will possess energy levels given as hc, b, which is the primary rotational constant, and then j, which is our rotational level. 0 if there's no rotational energy, and then every increased value is the next quantized energy level. And again, as a reminder, our rotational constant is mostly based on the moment of inertia. So in this case, for a linear molecule, we only have one moment of inertia that we have to worry about, because along the parallel axis, so that's right here along the center, everybody exists on the axis. There is no radii, so that is 0. So all we have to do is worry about end over end rotation. So for that, we can go ahead and calculate the moment of inertia. If you need a review, please feel free to go back to chapter 7. But again, larger molecules, higher moments of inertia, smaller rotational constants, more compressed energy levels. In practice, since we're using spectroscopy, we often like to present these energy levels in wave numbers. So this will be, again, our rotational term, as denoted from our rotational constant. Only major dependencies are going to be on J and the identity of the molecule, as that determines the moment of inertia. Now, one of the things to make note is that each of these energy levels has a degeneracy of 2J plus 1. So one of the ways to think about this is that I'm going to have, as I move faster and faster, I have more and more directions that that movement can be pointed in. And consequently, each one of those directions the movement is pointed in gives us a degenerate state. The classic example of this would be, say, with a J of 1. So this is my first excited state, slowest rotational movement. The movement can be pointed up, down, or in the XY plane. And as I go for my J value gets larger and larger, I can subdivide this more and more, and thus the increased degeneracies. Again, as a reminder, the J value also gives us an angular momenta. And an important reminder, the angular momenta has no dependency on the identity of the molecule, just on the rotational state. However, we can extend this idea to spherical molecules. Classic examples of this include things like methane or octahedral molecules such as hexafluorosulfate, so SF6. As these molecules, all moments of inertia are equal, so we still have only one moment of inertia, which means only one rotational constant. And again, as a consequence, that the rotational constant does not change, neither does the energy levels in joules or in wave numbers. However, biggest difference that happens here is we see a change in the degeneracy, because what I've introduced with a third rotational axis is more possible ways the molecule can move. And with more possible forms of movement, this is going to rapidly increase the degeneracy of my system. And as I go up in energies, I'm going to rapidly increase the possibilities and likelihood of being in an excited state. But again, angular momentum still shows no difference based on whether the molecule is spherical or linear. However, one of the things we have to watch out for is that most molecules we usually care about actually contain multiple different axes of rotation. So we're going to focus specifically on the symmetric molecules, so two different axes of rotation. So the moment of inertia about the principal axis is going to be given by I parallel, while the perpendicular axes, so these are our C2 rotations, are given by the moment the perpendicular moment of inertia. So this will be the notation that I'm going to make use of. We can also derive the energy level for the total rotation. So these are the total energy levels in wave numbers, is going to have a dependency on two different quantum numbers. J, which represents the overall angular momenta, and K, which represents how much of that angular momenta is along that principal or parallel axis. And so what we see is more or less our linear rotor equation for the energy out front based on our C2 rotation. So this is our classic tumbling pattern we see for linear molecules of the perpendicular moment of inertia. However, we introduce this extra K term where as K gets larger, I point the degree of motion out of the central axis, and I start replacing some of this end over end rotation with parallel rotation. And as a consequence, what I see is that my energy levels end up splitting. So so they'll split into two sets, one where the K is 0, and then a set where the Ks can range anywhere from negative J to positive J. So let's go ahead and look at this more in terms of actual physical motion. So our K really is distinguishing the direction of rotation. So if I have a K of 0, again, this is acting just like I've got a linear molecule, end over end tumbling. Whereas if K equals J, this means most of the rotation's about that primary axis. So let's go ahead and think of a good example of a symmetrical molecule. This would be a trans-isohedron. So essentially, most of my atoms along the central plane have all the same identity, but on the top and bottom, they have two different rotations. So my parallel rotation, this is going to be the highly symmetric one, is going to be the C4 rotation about my primary axis. But we also have the C2 axes going here and here. So if K is equal to J, most of the rotation is about the primary axis. K equals 0, all of the rotation is about one of these two C2 axes. In reality, often the rotation will be centered somewhere in the middle. However, one of the things that is important to note is how this K value acts on the degeneracy. So if K equals 0, we do essentially have a linear rotor. And as a consequence, we also have the same degeneracy as a linear rotor of 2J plus 1. However, if K is not equal to 0, then our degeneracy is going to be twice that. So one way to think about this is I've got a linear rotor, but one is going to be based on a value of K, and one is a value of negative K. So again, whether the rotation is in the forwards or backwards direction. And I do want to give a quick reminder of how K is different from M sub J. So K is all about the rotation with respect to this central axis. M sub J is always with reference to an external axis. So I have a large M sub J value if my angular momentum is pointed along an external z-axis. This is usually derived based on the measurement of a magnetic moment in an external z-plane. So again, note the difference in between Ks and M sub Js. M sub Js will never change the energy levels. Ks can. So with this in our back pocket, we're going to go ahead and see how these energy levels interact with our selection rules next time in rotational spectroscopy. Till then, take care.